Hi everyone. This is the video for sections 5.5, 5.6, and 5.7. 5.5, we're going to start off talking about substitution. So in certain cases, when you're trying to integrate a function, finding an antiderivative for a particular function can be difficult. If you have a function like x squared and you're trying to figure out its antiderivative, that's not too hard. But what if you have something like 3x squared times the square root of 1 plus x cubed, and you want to find the function for which, if you take its derivative, you get this, right? The antiderivative, in other words. So for these, we're going to kind of break up some of the work, and we're going to break up the work using a substitution. So here's our problem. So what I'm going to do is actually identify a piece of this problem such that if I take that piece's derivative, that derivative is present in the integrand. So what I'm going to do is let u equal the radicand here, 1 plus x cubed. Trying to make that focus. What I'm then going to do is to take the derivative with respect to x. So I'm going to take the derivative now, du dx, of my substitution. So that would be 3x squared. If I multiply both sides by dx, I could have du equals 3x squared dx. So what I can now do is rewrite my integral. So instead of the square root of 1 plus x cubed, I'm going to have the square root of u, right? Because I'm making that substitution. And what's nice about that is instead of dx times 3x squared, right? Here's 3x squared, here's dx. Here's 3x squared, here's dx. So what this substitution is suggesting is that I can replace 3x squared dx with just du. Okay, so I'll actually integrate this. I can find an antiderivative for this one more readily. And then what I'll do is I'll go back to x's. So this would be the same as the integral of u to the 1/2 power. So I can raise this power by 1. So it'll be u to the 3/2. And then we always divide by that new power. And then I'll have a plus c, since we have an indefinite integral here. So this would be equivalent to 2/3 u to the 3/2 plus c. And now what we do is we use our substitution in reverse. So now I'm going to replace u with 1 plus x cubed. So we would have 2/3 1 plus x cubed raised to the 3/2 plus c. As a check, remember what you can do is take this derivative and make sure that you get this integrand back. Right, so if you just kind of imagine that, I would multiply down, 2/3 times 3/2 cancels. Then we just have this raised to the 1/2, right? We lessen that degree by 1. And then I need to multiply by the derivative of the inside. So I would have 1 plus x cubed raised to the 1/2 times 3x squared. And that's exactly what we have here. These can take some practice to get the hang of. Here's another one. So I'm noticing we have a sine of x to the 5th plus 3. I have an x to the fourth outside of that sign. So maybe if I let u equal x to the fifth plus 3, good things will happen. I'll go ahead and take its derivative. I'll also just multiply over by dx simultaneously. So 5x to the fourth and then dx. So what's going on is, well, I'll be able to call this now u instead of x to the fifth plus 3. I'll substitute that out. Here, in my derivative of my substitution, I get a 5x to the fourth. Here, I only have an x to the fourth. So what I want to do is solve for x to the fourth. So maybe I'll divide by 5 here. So what that would mean is 1/5 du would be the same as x to the fourth dx. So x to the fourth dx can be found right here. So x to the fourth dx will be substituted out for 1/5 of du. So this new integral would be sine of u times, instead of x to the fourth times dx, I have 1/5 of du. Okay, so we need to kind of make that adjustment. In the first one, there was no adjustment needed because our derivative was exactly what was present. So there was no kind of adjustment necessary. So one of our properties of integrals is you can pull out any constant factors. So I can say 1/5 and then just sine of u du. Antiderivative of sine is negative cosine. So this would be 1/5 of negative cosine of u plus c, since this again is an indefinite integral. So this would be negative 1/5 cosine of u plus c. And now again, going back to what this problem cared about in terms of variables. So we would have negative 1/5 cosine of x to the fifth plus 3 and then plus c. All right, let's try another one. I'm going to skip down to example 4. All right, so looking what we have, kind of difficult to think of what an antiderivative would be for this. So I think a substitution may help. So I'll let u equal, I'm noticing that I have a quadratic inside of here and I have a linear term up here. So if I take the derivative of this, I will get a linear function. So that kind of suggests that this might be our substitution. We may want to let u equal 2 minus 3x squared. So this is the kind of thinking a move ahead part of these is I'm noticing, oh yeah, I have a quadratic. If I take a derivative, we knock down a degree, and then I have a linear. I might just need to offset it with some constant correction. Right, so du equals negative 6x dx, right? I'm taking the derivative with respect to x, but then also just multiplying over by dx. So what I see is I have a negative 6x dx, but I just have an x over here. So I need to solve for x dx. So I'll divide by negative 6. So in other words, negative 1/6 du will substitute in for x dx. So x dx is right here. Okay, just to kind of rewrite our integral so you can see what I'm talking about more clearly. times x dx, right? This would be the same as our original integral. So here is the part that I'm substituting out, right? We're going to substitute that out, and we're going to replace it with -1/6 du. And at the same time, I'm going to have 1 over the square root of just u times -1/6 du. All right, so I can pull out the -1/6. I can rewrite 1 over root u as u to the -1/2 du. And finding an antiderivative of this integrand is not too bad. So I'll have -1/6 u to the 1/2 divided by 1/2 plus c. And then eventually I'll need to go back to x's, of course, but let's simplify this. So 1/6 divided by 1/2, this would be -1/3 u to the 1/2 plus c. In other words, we would have, let's see, -1/3, and u is the same as 2 minus 3x squared. I'll just go ahead and write the 1/2 power as a square root. So 2 minus 3x squared plus c. All right, I'm writing plus c on all these because so far these have been indefinite integrals, meaning no limits here and here. Here is one where we have a definite integral. So let's try one of these out with a definite integral. So I'm going to let u equal 1 plus 6x. du would equal 6 dx. Right, I don't have the 6, so I need to solve for just dx. I'll divide by 6. So I would have 1/6 du equals dx. So where I have dx over here, I'll replace that with 1/6 of du. Let's go ahead. So I'm just going to write stars here actually for a second. When you're making a substitution, your original limits actually don't apply directly. So I'll show you what happens there in a second. So we would have the cube root of u, right? Because I substituted out that 1 plus 6x. And then instead of dx, we're saying 1/6 du. Okay, so this would be the same as 1/6 integral of u to the 1/3 du. This would now equal 1/6. I raise this power by 1, so I'm going to have u to the 4/3 divided by 4/3. I do not need a plus c. We're going to evaluate this at our limits, right? This is a definite integral. So let's clean this up a bit. So 1/6 divided by 4/3, what would that be? 1/4? No, let's see. 1/8. So we'll have 1/8. U, I'll go ahead and rewrite it. So now we want to go back to x's. Okay, so I'll have 1/8 of 1 plus 6x raised to the 4/3. And then I'll evaluate that from 0 to 1 since that was our original limits. I hadn't written the limits because we're now in the variable u, and these limits only pertain to the variable x. So I actually didn't want to write 0 and 1 because 0 and 1 don't apply to the variable u, they apply to the variable x. So it's not until you go back to x's that you want to evaluate actually at 0 and 1. So we would have 1/8, and now I'm evaluating at 1, subtracting, evaluating at 0. So 1 plus 6 times 1 raised to the 4/3 minus 1 plus 6 times 0 raised to the 4/3. Let's see what this is. All right, so we'd have 7 to the 4/3 and then minus 1. So I'll keep this in exact form. Maybe I'll write this up here. So 1/8. This is my 7 to the 4/3. And I would be subtracting 1 over here, right? 1 is the only thing that's left. 1 to the 4/3 is 1. So this would be my exact answer. Keep in mind your calculator, if you have one of these, your calculator can do a lot of these. Not every instructor will let you do this, so don't abuse this ability, but this is a good way to check your answer. So if you press this integral, first off, I believe if you're in complex mode, the integral won't work. So you need to be in this regular computational mode. So that was mode and then number 1. So integral, and then I'll type this in. So I have the square root of 1 plus 6 times, and then to access x, it's right here. So I'll go alpha right parentheses, scroll up, 1, down, 0, press equals. It's going to give you an approximate. Again, another reason why this is not a great way to produce all your answers. But if you just memorize real quick that number, let's type this in to make sure it matches. And does it not? Let's see. Let's type in the integral again. I'm getting something slightly different. Let's see if I can catch this. Third divided by 4/3. 1/8. I can't find it. So maybe in the video discussion, you guys can find this. So let me know. Maybe I'll come back to it. Another way that I could have done that problem, and maybe this will be what I actually do. So I'm going to introduce this other idea. So let's say I was right here again. So right at this stage, where I have 1/8, and then I would have had u to the 4/3, and then evaluated from star to star. So what I did do was I basically went back to x's. There is a workaround. You don't need to actually go back to the original variable. What you can do is plug in your limits to your substitution to define new limits. So what we want is to adjust this appropriately. So before, my bottom limit was 0. So plug in a 0 here, and you get a 1. So 6 times 0, 0 plus 1, 1. So 1 would be your bottom limit if you just stick with u. Okay, plugging in a 1, right? That was our original upper limit. So plug in a 1 here to figure out what your new upper limit is in terms of u. It'd be 7. So plugging that in, we would have 1/8 times 7 raised to the 4/3 minus 1 raised to the 4/3, and that would just be 1/8 times 7 raised to the 4/3 minus 1. So that's what I'm getting again, but please comment in the video if you find a mistake. I don't want to take up too much more video time. Okay, let's try more. A couple more from this section. Here's another definite integral case. All right, so we have this going on. By the way, this would be the exact same as this integral. Okay. So sometimes you'll see people write dx on top. That would be the same as 1 and then dx on the side. So what I'm going to do is let u equal ln of x. Then du would equal 1 over x, and then I'll multiply over by dx. Okay? So we actually have exactly what we want. Here's 1 over x, here's dx, here's 1 over x, here's dx. So this can all be substituted out without any kind of counter adjustment. So I can rewrite this integral as 1 over the square root of u du, right? Because literally 1 over x dx is du. Here's 1 over x dx, here's ln of x, right? All this stuff gets substituted out. If I want to change my limits, which I encourage you to do, actually, I think it saves work. So plug in e to your function here, right? So this lower limit will be ln of e, which is 1, right? So what I'm doing is I'm plugging in this right here. ln of e is 1. Then I'm plugging in this right here to see what our new upper limit is. So plug in e to the 4th into ln of x, we get a 4. So this would be equal to the integral of u to the negative 1/2 du going from 1 to 4. So raise this power by 1, divide by the new power. So just to save a little bit of work, we'll get 2 times u to the 1/2, and then I'll evaluate that from 1 to 4. We're going to check this one too, just to make sure that math is working. So 2 times 4 to the 1/2 minus 1 to the 1/2. In other words, 2 times 2 minus 1. In other words, 2. Let's type the original one in and see if the calculator can do it. Maybe it can't. Sometimes the calculator breaks down a bit when these get more difficult. So I'll go 1 over x square root ln of x, end parentheses, scroll up, e to the 4th, and then e. Let's see what happens. Calculator's thinking. Just Thinking a lot. The calculator's starting to sweat now. We got a 2. All right. Good deal. All right, so in certain cases, you can get fancy. So keep in mind that you're finding areas under curves. You're finding like the net change of the area under the curve. So if you have a symmetric area, like imagine this curve, we're going from -5 to 5. This is similar to a parabola. It's not a quadratic, it's a quartic function, but it kind of looks like that. So we'd have this essentially. And if you're going from -5 to 5, then this area would completely match this area. And because of that reason, I can change this integral. I can rethink it as twice going from just 0 to 5, x to the 4th plus 1 dx. It's nice to do because plugging in a 0 into your antiderivative is easier than plugging in a -5, and then doubling just produces the same amount of area. So I can write now 2 times x to the 5th divided by 5 plus x, and then we'll evaluate from 0 to 5. Right? Right, so I increased by 1 degree divided by that new power. Increased by 1 degree divided by that new power, technically. So 2 times 5 to the 5th over 5 plus 5. So I'll use more parentheses. So that's evaluating at 5. And then I subtract that second fundamental theorem of calculus, plugging in at 0, which this is kind of the reason why we did that, because now I'm just going to get a 0 here. It just comes down to this stuff. So just doing some calculator stuff here, I get 1260, it looks like, on the calculator. And again, if I wanted to check that, integral there we go. All right. Let's go on to 5.6 and 5.7. 5.6, integrals involving exponential and logarithmic functions. Here's a couple kind of need-to-know formulas. Let's go on to example 2. So I'm going to, again, use a substitution, actually. So I'll let u equal 1 plus e to the x. That way du is actually just e to the x dx, right? Derivative of e to the x is itself. So I have e to the x dx, e to the x dx. So this substitution looks nice. We'll have just the square root of u du. Right? This is an indefinite integral. So now actually finding the antiderivative, I'll have, well, maybe I'll think of it as a power first. So raising that by 1, dividing by the new power, I get u raised to the 3/2 divided by 3/2 plus c. And then going back to the original variable, right? That question didn't ask anything about the variable u, it asked about x, so I'm now replacing that. So I'm going to take this and plug it in there. So this would equal 1 plus e to the x raised to the 3/2. I guess I'll say times 2/3, because dividing by 3/2 same as multiplying by 2/3, plus c. All right, restarting. Jumping to page 122, example 5. It says evaluate the definite integral using substitution. Okay. So I'm noticing 1 over x as a power x squared in the denominator. So if I let u equal 1 over x, then I would have du equals, well, if I think of this as x to the -1, then I would have -1 over x squared dx as my derivative. So I do have the 1 over x squared. I do not have the negative. So I'll divide by that negative. So in other words, negative du will equal 1 over x squared dx. So all of this stuff is here now, there and there. The only thing I'll need to do is offset this by this negative. So I'll have e to the u. Everything else is gone except I need a times -1 du. If you want to switch your limits, you can, or you could stick with 1 and 2 and just go back to x's and use 1 and 2 at the end. What I'm going to do is make a switch. So what you do to make that switch, just to remind you, is you take the original lower limit and you plug that into your substitution to see what your new lower limit is. So 1 over 1 would be 1. So actually it's still 1. Then plug your upper limit into your substitution to get your new upper limit. So plugging in a 2, I get a 1/2. Okay. This would be equal to -1 to 1/2 e to the u du. There's a property about definite integrals that says if you switch the limits, then you need to make the opposite sign. So if I switch these actually and get them in the proper order, notice this one's larger than this one. Usually we want this one to be less than this one. So if I switch these, I can negate. So this would actually be totally equivalent to 1/2 going to 1 of just e to the u du without the negative sign. Not a necessary step, but it's one you can make. And now the antiderivative of e to the u, the antiderivative of that would be itself. And then I evaluate from 1/2 to 1. So we would have e to the first minus e to the 1/2. In other words, e minus the square root of e. That would be the exact form of your answer. Okay. Just gonna do 2 more. Let's look at this one. This is on page 124. It says evaluate the definite integral using substitution. All right. So I'm noticing a sine, a 1 plus cosine. So if I let u equal 1 plus cosine, I think good things will happen. So u equals 1 plus cosine of x, then du would equal negative sine x dx. And that's nice because I have sine x dx. I don't have the negative, so I'll need to offset that by -1. So I'll have that negative du is the same as sine x dx. Okay, so I can make all my substitutions now. We have 1 over u. Instead of sine dx, I have -1. So this is like multiply -1 times du. Again, if I want to switch my limits, that's a good option. So I take this lower limit, plug it in here to see what my new lower limit is. So cosine of 0 is 1. 1 plus 1, we have a 2 now. Plug in pi over 2. Cosine of pi over 2 is 0, plus 1, we get 1. So this would be equal to negative u to the -1, I'll say, from 2 to 1 du, right? And again, similar to a previous one, we can switch these limits. We have a negative out front, so it would switch and just become the positive. So we're looking for, if I just go back to 1 over u, I kind of want to do that for some reason. So 1 over u du, we're looking for a function such that when you take its derivative, you get 1 over u. So back here, I kind of flew past it, but on page 123, there's these formulas. Okay, so x to the -1, same as 1 over x. That antiderivative would be ln of x, right? Take the derivative of this and you get this, actually. So ln of absolute value of u, and then we need to evaluate that from 1 to 2. All right, I'm just checking in on everything, making sure I'm happy with that. I think I am. So this would equal ln of 2 minus ln of 1. So this would equal ln of 2. Interesting, okay. There's that one. On to 5.7. I'm not going to talk much about 5.7. There's just a list of formulas you kind of need to know how to work with. Here they are. So I'm just going to do a problem and call it good. So looking at the possible formulas we have, this would be like, let me just rewrite it. 0